Okay, so we talked about description of phenomenological models of viscoelastic materials, which are combinations of springs and dashpots. And we talked about a Maxwell, a Kelvin, and a Berger body. What we'll go through today are Newtonian and I think a Maxwell. Let's see. Yeah, Maxwell and Newtonian fluids, and introduce actually the governing differential equations and show how those work. And then we'll be looking at two conditions: one, constant stress, which would be creep, and two, a cyclic stress condition, which would be like a DMA. And we'll do that for both the Maxwell body and a Newtonian fluid and see how they're different. Then on Thursday, I think we'll get through this today. On Thursday, we'll move on to the Berger body model, show that, and then start to work with how you can estimate these parameters from experimental data and work the other way. So here is just predicted behavior, and then we'll look at how we can get models from experimental, get values from experimental results. Because if we want to know what the E of a material is, we do a bending test, or we do a tension test, we measure things, and we have our simple P over A or PL cubed over 48, whatever the equation is, M over S, and we calculate what the E is. For these parameters, we have multiple parameters, so we'll see that there's more involved. So we'll show how to do that and how to compare. All right, so Newtonian fluids. I think we talked about this, is that the differential equation, we said we had stress over, we said for an elastic material, stress over strain is a constant, and that for a Newtonian fluid, stress over strain rate is a constant, and we said that that constant is the viscosity. So we said is, right, stress over, might as well put this in here, stress over strain rate is equal to a constant. So in a functional form, what I've done is now I've taken stress and strain rate, which is a derivative of time, so we multiply that, and this is our typical differential equation. Differential equation, we have the derivative of strain with respect to time. So that's what and in general, the stress can also be a function of time. It could be a constant, it could be a ramp load, it could be, so we'll look at two cases, a constant and that it's sinusoidally varying. But it could be a ramp load or anything else we might want to have. Okay, so that's the governing differential equation. And let's look at the case where we have constant stress. Solve this differential equation and then look at its behavior over time. And we've already talked about it graphically. We said it will be a straight line, right? Zero deflection at time zero, or strain at time zero, and increases linearly. But let's do this on a more rigorous mathematical basis. So again, we're gonna start out and say the stress is some constant value. I'll just say sigma naught. And so what we can do is substitute our value of sigma as a function of t as a constant. So all I've done is take this value of sigma naught, plugged it into here, and we get this equation, that a constant stress is equal to the viscosity times the strain rate. So this is a specific case of the general situation. So we don't measure strain rates. We measure strains, or we measure deflections. We don't measure deflection rate. So what we need to do is integrate this equation so that we can say, well, what is strain as a function of time? Because that's what I'm measuring. So we need to change that. So in order to do that, what we need to do is integrate this equation So we're going to go from strain rate to strain. So that is, we're integrating with respect to time. And we're doing that, we're integrating with respect to time of the two sides of the equation. Now in this case, our viscosity is a constant and our stress is a constant. So we could pull that out of the, I actually didn't do that, but we could pull that out of the, we pull that out, and then the integral of blank dt is t, and the integral of the strain with respect to time, of strain rate with respect to time, is the strain is a function of time. So this is as easy as it gets. But it's probably been a while since you did this kind of thing, if you did this thing before. So you haven't had differential equations yet. No. Anybody else have you had differential equations? You've had it. Have you guys had differential equations?
Yes.
Yeah. Middle school?
No,
Yeah, it's high. Yeah, I went to high school too.
Yeah.
not differential equations.
But I'm sure we carry
Usually, when I was in college, that would be you do 3 semesters of calculus and then you do differential equations. And I think that's typical. That's the way it is here. And
It's simple. Interlining high school, but differential equation was something I need calculus 1, calculus 2, that's a
yes,
Yeah.
yes, homogeneous equations and all of this kind of stuff, and yeah. Yeah. And then you take partial differential equations, because that's what is really useful. And that's your next math course. But this is, well, you'll take my word at this. So if we just look at this, but that's why mathematics is nice. We'll be able to see graphically kind of what's going on, and I think it's really useful. So if we look at this, if this is constant, then we can just see strain is going to, it's going to be a linear function of time, and the slope of the line is just going to be that constant, the ratio of the stress to the viscosity. So you're old hats at this, right? We can define our function. Strain as a function of time is going to be that. And now I'm just going to plot the function strain. I'm going to give a value of viscosity or of stress, it's 10. I'm going to give a viscosity value there and t, and I'm going to let t go from 0 to 100 seconds. And yes, it's a straight line. Starts at 0, and that's what we had given you before. So if we think in terms of viscosity, units, we talked a lot about units early on. Well, what are the units? In the imperial system, we could say psi seconds. Useful when we talk about modulus of elasticity being pounds per square inch. Or in SI, it would be Pascal seconds, typically. So the units for E of a material in the SI are going to be seconds. You could say Pascal hours, but typically we talk about seconds. Often in the US we talk about centipoise. and 6,894,775 centipoise is 1 psi second, which has a name of Ren, if you're using English or imperial units. But we often see centipoise in the US. What's the viscosity of water at 20 degrees C? 1 centipoise. Okay. So we'll kind of play with some of these numbers. And so what we had up here is 50 psi. That's pretty dang viscous. All right, so that's 50 million times the viscosity of water. And here is strain. So these are realistic strain values. We'd call that as 0.3% of strain. Wood fails at maybe 3% strain, something like that. It depends. So we're just kind of making up those numbers. But if we put in any other number, let's just make that 1. It's going to look the same, but now it's going to be 10 times more per unit time. So, all right. So that's pretty simple equation. You don't need Mathematica for that. That's the behavior. And now you've got the solution of that. So now you could do it algebraically. Now the question is, so let's get rid of that. Let's go to the case of cyclic stress, which is often what's done in DMA. And so let's look at one case here where it's sinusoidally varying in this omega. This is called our angular frequency. Do I talk about that up here? Let's just add this in. Is typically termed the angular frequency. If you take a course in vibrations, you're always talking about the angular frequency, and instead of saying how many in hertz, you typically, anyway, this is the way it's typically dealt with. So what we can do is just say, now here's our governing differential equation. The stress as a function of time is given by this. So we just dump this into here, and then I'm pulling the viscosity over on the other side is equal to our strain rate. So we're just manipulating the equation, substituting, rearranging, and just as before, I now have strain rate. I want to know strain. So I have to integrate both sides. So I integrate the left side, I integrate the right side, and I know that's going to be strain as a function of time. And so now I need the integral of sigma naught sine omega t over the viscosity. So it's the same approach that we did with a constant, but just a slightly more complex function. So if we go back to when you integrate something, you will then have a constant of integration that comes out of that, which we can say is C1. And there's a couple different things that we can have in Mathematica to solve things. We'll use one called the integrate function, which doesn't give our integration constant. And then I'll show you a numerical form that will give us our constant of integration. And we can solve, because the constant of integration will be dependent upon boundary conditions that exist. So, but let's not worry about that first. There's a built-in function in Mathematica to integrate functions. So we're integrating. Actually, that should be over. Right, that should be divided by viscosity, right? Sigma naught sine omega t over n, and we're going to integrate with respect to t. So that is the integral minus stress cosine omega t over the viscosity and again the frequency omega. You don't need to remember that. There we go. And of course, then you would have a constant of integration. But if we ignore that constant of integration, all I do now is I take this and plug it in for here, right? That's my integral. So strain as a function of time is the integral minus that over there. I've pulled this out separately, 1 over omega cosine omega t. And again, in this case, this is constant, and this is all constant, and this is our time variant. So if we plot it, and I'm just going to, so we're plotting, here I'll say in terms of A. So here is our stress as a function of time, right? Sigma naught sine omega t, I'm just going to say A sine bt. And we'll have an amplitude of 100 and a frequency of 2 pi. And then a viscosity of 1, and then we're also going to plot minus the stress divided by the viscosity times the angular frequency. I'm just going to throw another parentheses in there to make sure that that's on the bottom. So that should be this. That should be this function, and then our original function. Let's see what this looks like. So this should be sine at time 0 is 0. So it should be a sinusoidal function, starts at 0, and the amplitude will be whatever the value of A is, because the sine function goes from -1 to 1. So our amplitude, we said A is 100, so here's our applied stress going up to 100, down to -100, and back to 0. Got a frequency of 2 pi. So if I just go to time of pi, let's just play with this. Yeah, I should have 1 cycle, 3.14. 2, 3. Oh, okay. So I should get 4 of those. Yeah, going after pi. So we should get 2, 1, 1.5. That's a half. Yeah. So anyway, And if our frequency is 3 pi, so you can play with that. But what's really interesting now is here is the strain. This is not at 0. It should be starting at 0. It did earlier. And this should be 0.
Right under the tick mark is 0.0. I don't think it's on that axis. It starts to lie over.
The second function because of the cosine is 0 up to
Yeah, it is. It was on my other computer all day, and it never was not at 0 when I did this. Because it needs to be at 0. What it's possibly changed because it was 0. I've gone through all of this. I mean, they both should be 0. Unless this is,
Well, do you have to see added for this time? If you add that one to cosine, it will be 0. Cosine C.
sine. So that's right. I mean, that's 0. Oh no, I'm wrong. Well, that's where this will come in. This will come in later. It needs to be 0. That's why we'll have the constant of integration. We'll put it to 0. That's what I think. So the point, or a key point, is that the maximum here is going to be lines up over where that's 0. So this is the same form, but it's shifted actually 90 degrees or pi over 2 radians. Yeah, it's a negative strain. So what we've got to do is we've got to move that up to 0, and that's what our constant of integration will do. So what we do, so if it was a spring, the peak here would line up under here. We got a dash pot. It's shifted. Phase shift is 90 degrees, or pi over 2. But we know that at time 0, the strain has to be 0, and therefore the constant of integration is this. That will be equal to that offset. And so this is the equation for strain, the function of time for a dash pot with a sinusoidally varying load. I'll give you the files, the mathematical files. But let's plot this out. So I've got the same thing, but I've added the constant of integration. And when we plot that, they're zeros. And we got the phase shift of the 90 degrees. But now what this will mean is that even though we have a negative stress, we never get a negative strain. Well, it's incompressible is part of the reason. But then if we think of a shock, we can think of about we got the phase shift. You think about, say, a shock absorber. When you push it, you have to apply a force in order to move that, and then you have to apply a force to pull it to you for it to come back. So that might be a way, kind of a mechanical way of thinking about how we've got a negative stress, but we never get a negative strain in this case. So that's a fluid. We're going to introduce you to another function that solves the differential equations directly, rather than what we've done up here is, in essence, kind of doing it by hand, the old-fashioned way, doing it on paper. What is it? And then we're just plotting things. So when I was in school, right, you had engineering paper and you plotted everything by yourself with a ruler, and that's why you had your French curves, and that's why I'm so impressed with this, because it saves you so much time. But we can also, there's a built-in function called differential solve that solves our differential equation. So let's take a look at this. So here's the command, dsolve, and this is what we're solving. The derivative of strain with respect to time, so E prime, often, okay, that's our first derivative. And if you had a second derivative, I mean, it'll take care of second derivatives too. But first derivative is identically equal to sigma naught over neta sine omega t. I'm solving for strain. Again, it might be you have a double derivative in a function. You want to solve for the first derivative. I mean, that's why we're explicitly saying we want strain as a function of time, and our variable there is time. So if we do that, there we go. Strain as a function of time is constant of integration minus, so it's the same thing that we had before using the integrate function. Okay. So that's a dash pot, and we've already done the spring, which we know there is no integration going on. It's just a direct response. So now that we've defined these two responses, everything now is adding these two elements together. Before we move on, any questions about that? Okay, so let's go to the Maxwell body and do the same thing. Talk about our governing equation, solve that differential equation for the case of constant stress, then solve the differential equation for the case of cyclic stress and see what happens. Right? And so the differential equation, and I believe I handed out the PDF write-up that I'd put together some years before that gave the values of P1 and Q1 and the different differential equations. That we didn't talk about it in class, but I handed it off to you. But this would be, in essence, a standardized form. So on the left side of the equal side are the stresses, and the right side are the strains. Well, I did give you the differential equations in class, but we didn't actually solve them. So you've seen this already. Stress plus a constant times the stress rate is equal to a constant times the strain rate. That is the differential equation when we have a spring and a dash pot in series. Q1 is equal to the viscosity. P1 is the viscosity divided by the E. So we're just taking our physical constants of the spring and the dash pot, rearranging them slightly to create this standardized form of the differential equation. So what we want to do is solve this one, which is a little more complex. Well, now we've added this term, right? Before we had stress is equal to a constant times strain rate. Now we've got another term in there. Let's see what happens. And we'll use this D-solve, which we saw, I introduced you to, which was a symbolic solver, but there's also a numerical solver that will give us the actual numbers for doing that. So we'll show both of you, both approaches to this differential equation and see what happens. So let's take a look at the constant stress condition, and that is stress is a constant value. And the stress rate, a derivative of a constant, is 0. So this right here, for constant stress, will drop out because sigma prime is 0. And therefore, it's just going to be sigma plus Q1 times the strain rate. Will be a simplification of this equation for the case of constant stress, and that's what we have right here. So let's use the symbolic solving capacity of Mathematica to find out what that is. So again, this is, and of course you can go up to your help, go from documentation, and we'll type in D-solve, and you'll get all kinds of things. So here, your partial differential equations, all that stuff, will take care of it. So this would be the derivative of y of x plus y of x is equal to a times the sine of x. And there, it does that. And let's, again, the nice thing here, I could change that to cosine in here, and it'll interactively, you start playing around without messing around with your files. So anyway, let's see what we get. So we got the strain rate is equal to sigma over Q1. We're going to solve for strain as a function of time. And this is the solution. Strain is equal to a constant of integration plus time times sigma over Q1. Q1 is viscosity. But again, we've got a constant of integration. How do we find out what that is? D-solve will solve it for us. if we give it, that constant of integration again depends on our initial value problem or a boundary condition, and typically we know initial values. So let's just compare here. D solve, so the derivative of strain with respect to time is equal to stress divided by Q1. And what I'm doing in here is I've noticed the curly brackets, I'm adding a boundary condition or an initial value. I'm saying the strain at time 0 is equal to 0.05, or let's just say that it's equal to 0. And I solve it, and in that case, if the initial displacement, initial strain is 0, the constant of integration is 0. If I have an initial value, let's say 0.05, this then is the analytical form of the solution. What is the initial? What's the correct value? What's the initial value for the spring and dash pot series? What's the time, the strain at time 0? Pardon?
The series?
Yeah. So it'd be, let's see, stress over strain equals E. So strain is going to be stress divided by E. So let's see if I can do this symbolically. Let's say stress, let's make this, I'll say stress divided by strain. I'll just say F over G. Okay, there we go. F over G. F and G comes in to the solution, in that case symbolically. And you could then simplify those kinds of things, okay? So that gives us a closed form solution, which you might want to do, but we can also calculate the actual values directly rather than taking this function, then creating a function off of this and then plotting and all those things. We can do it directly. And that's what's called ND solve. That's the built-in function in mathematically to numerically, the numerical version of differential equation solver. So let's look at the case. What we need to know is the applied stress and the value of Q, 1. That's our unknowns. The stress and the value of Q1. So I'm going to say, let's give them these numbers, 1,000 and 50 million. Let's say that we got an MOE of 10,000, therefore the strain at time 0 is going to be stress divided by the E. So here's the form. The strain rate is stress divided by Q. The initial strain is equal to the stress divided by the E. Solve for strain as a function of time. And let's do this for 10,000 units of time. There we go. Now I'm assigning it to a variable, and I can now, here's a context, I'm going to plot, and I'm going to evaluate, in this case, it's strain as a function of time. Strain of time is I'm going to refer to this solution here. I could just put all that in directly, but this is a, let's just see what we got here. It's another way to plot it. So at time 0, I have a value of 0.1, which should be stress over strain is 1,000 divided by 10,000. Okay, so it starts out at 0.1. That's the spring, and then it increases linearly. That's just what we talked about in class 2 weeks ago. But now we have this and show how we get that based on the boundary conditions or the initial value problems from the governing differential equation. And if I made, okay. So let's get to the more interesting case, which is going to be cyclic stress condition. Good. I planted stuff in the garden over the weekend. This rain is good. This rain is good. So in talking about cyclic stress, we had said before that the spring and stress and strain are totally linked, and so the maximum of strain and the maximum of stress line up one behind another, or one over another. We said for the dash pot that there was that phase shift of 90 degrees, pi over 2. So we're taking an element that has no phase shift, and we're taking an element that has a pi over 2 phase shift, and now they're working together. So what we'll see is we'll have a phase shift somewhere between 0 and pi over 2. And the amount of that phase shift will depend on the ratio of the spring to the dash pot. The more, if you have a very small e and a very high, if you have if your ratio of viscosity to E is high, it will act more like a fluid, and your phase leg should be more towards pi over 2. If your viscosity to E ratio is very small, the phase shift will be more towards 0. It will be more elastic material. And that's what you do in a DMA, is you measure the phase shift, and then you back calculate then what the response of that material must be by measuring that phase shift. So anyway, let's go through the math. Where did that go? Anyway, we're going to add those two together. Sum of the strain in its dash, I don't know where that went. Anyway, let's take a look at this. So I'm going to define my E and my viscosity. I've got my parameters, P1 and Q1, and I've got my frequency, and I've got my initial stress. Those are the parameters that tie in. So I'm going to numerically solve my equation as the strain rate is now, instead of it, this term had dropped out in the first case because we had stress was a constant and the derivative dropped out. But in this case, these all stay in. I should get that up there. Where did that go? P1, Q1. So now I'll add it in later, so your notes are going to be complete. Well, this is the function. Sigma naught over Q1 sine omega t plus P1 omega cosine omega t. Our initial condition, I just picked a value. Let's make that, we'll start out at that being 0. We know that's not right. Let's just put in a value. That would be our initial strain because of the, well, I'll make that 0. We'll see what happens. I'm going to do this for 100 seconds. And then I'm going to plot it out over 40 seconds. So let's just do all that. And here's the curve that I get. So at time 0, I've got 0 strain. Stress goes up. And this seems to be pretty much in phase. Here's our stress. Here's our stress here, and here's our strain. And our maximum, so this is acting very much like a spring. Right? It's in phase. Let me just talk a little bit about here. I added a command, it's called timing, and then I put a bracket around everything. So it took 16 thousandths of a second to evaluate everything within that range of 0 to 100 seconds. I always like to do this. If I go over a range and it's numerically evaluating over 100,000 seconds, it takes 0.69 seconds. And a million, I think, goes to 8.8 seconds on this computer. It's 2.6 on my. And then you can parallelize this, and it'll use 8 cores or 16 cores and do all that kind of stuff. But that's then you get lots. And anyway, this is acting very much like a spring because there's no phase shift. So what we could do is let's drop that down to 1. An E of 1. So that should make it be more fluidy. So I'd expect that we'd see some kind of a phase shift. So we did. Let's see what happens. I hope I'm right. Yep. See, now our peak has moved over to the left. Whereas when that ratio was 1,000 to 1 of E to viscosity, this lined right up. So now if I let's make this so I'll expect to see more of a phase shift if I soften that material, if you will. Well, we've got some scaling issues here, but that's moved now. Initially it was over to here, now it's moved over to there. So that's what we talked about. Actually, we don't even, I'm going to just ignore all this. It kind of gets in the way. I'll just do this. You don't need to worry about it. If you have an interest, you can look at the code later, but this is showing, again, I've changed it around, so this is showing those phase shifts for the parameters that we had up there, and you can actually determine what that relative phase shift is. So again, that's what your DMA will measure that phase shift and then back out and say here's what your reduced modulus, which is in essence your viscosity is. Okay. All right. Well, that's the Maxwell. So we've done those two. And we're going to move on now to start in on the Berger body. And in this case, I'm not going to, we'll take the other tack, and we're starting to move in now on if we run an experiment, how can we calculate the values of these parameters for the case of the Berger body? Because when you've got a lot of polymers and it's highly, and you've got a more pronounced viscoelastic response, Maxwell model is fine, or Kelvin model is fine, but it doesn't work for composites, for solids. The Berger body is more often used. It doesn't work very well either, but it works better. So I want to show you how you can do that. And then on Thursday, we'll actually have some data files and from some work that's been done, and we'll look at that and see how that happens. We've actually got like over a year's worth of data on some of these, so we'll want to look at different amounts of time and see how good the predictions are. So let's get back to the Berger body, and the Berger body was the Kelvin and the Maxwell in series. So you had 2 dash pots and 2 springs. Spring in series with a dash pot, in series with a dash pot and spring in parallel. And they were the elastic, viscous, and delayed elastic components of creep, respectively. So we're looking to, from experimental data, find out what those 4 parameters are. 2 spring constants and 2 viscosity values. And it would be possible to do this for cyclic conditions or for stress relaxation conditions, but we're going to do it for the case of constant stress where we have creep. Again, that's the typical thing that you do in the laboratory. You hang a weight onto something and you just go weigh it and measure it. So we've been talking up till now about stress and strain, but we typically measure loads and deflections. So I want us to pull in the work that we did before about beams and kind of combine those two. So if we look at the case where we have a beam with a concentrated load at mid-span, we have this equation where stress is moment over section modulus, maximum moments PL over 4, that's pH squared over 6. Anyway, that's our equation for stress. Maximum stress is a function of applied load, span, width, and depth of the beam. Now what about strain as a function of applied load? So we know that stress over strain is equal to the E. And for that load, we know that typically we say deflection is PL cubed over 48 EI. So all I've done is flop the delta and the E, and so E is equal to PL cubed over 48 deflection I, again, if we are in the linear range. So here's what, so now I know then that strain is going to be, just algebraically, if I want strain, that's going to be stress divided by this. And stress is that. So here's stress divided by strain is equal to this, and I've expanded the moment of inertia again to be in terms of B and H. And go through all that, and here's now your estimate of strain. Is the deflection 6 times the deflection times the height divided by the span cubed. You don't usually do this. What's the strain in a beam? I mean, that's not a calculation you typically make. But this is how it works. And then if you've got a different kind of beam, right, you would have a different equation here and a different moment here. And if you had a circular cross-section, you would have a different moment of inertia and radius. But that same approach will let you determine what the strain is as a function of deflection. Notice it's not a function of load, it's a function of deflection. Whereas the strain in axial tension, right, is change in length divided by the original length. In this case, it's 6 times the change in length, or the deflection, divided by the span cubed. So very different equation. So, and I'll need to copy a chapter out of Bodig and Jane. I'll scan that and send that to you, which gives you these equations. But if we went through the differential equation for the Berger body, did the boundary initial value problem, solve for constant stress, we would end up that this would be the solution of the differential equation. Okay? I'm not using Mathematica to derive that, I'm giving it to you. If we wanted to know what the differential equation, what's the solution of strain if we had a cyclic stress, I'm going to have to go back to Mathematica. And in this case, we have now our 4 constants. The spring, that's the spring, the elastic component. Here's our, so this represents our elastic strain. So this should look familiar. This is our strain of the dash pot, or our fluid, right, which is stress divided viscosity times time. So that's what we looked at already with the Newtonian fluid, or in essence, these two together is the Maxwell. What we have here is the Kelvin. That's the spring in the dash pot in parallel. And there we have an exponential function. And this term L, or lambda, is called the relaxation time, which is the ratio of these two parameters. So anyway, that is the solution to the differential equation for a Berger body for creep. So I'm just going to, let's see how this looks. So I'm going to, here I'm just taking out this part of it, the delayed elastic part of it. So it's 1 over E times 1 minus E to the minus T over lambda. I'm just putting these numbers in here. But this is just the delayed elastic. So I'll define that function, putting some numbers in it, and then I'm going to plot it. And this is going to be, what's it going to look like? What strain is a function of time for the spring and dash pot in parallel under constant load? Let's see. Initially 0, increasing, and reaches a constant value. This constant value is the spring. That's our limit. And the rate at which we get this kind of a curve depends on the ratio of the viscosity to the spring. This this ratio here, what's called the relaxation time. That controls the shape of this curve. But it always starts at 0 and goes to an asymptote. So if let's just play around with this. This is the relaxation time, right? This is this lambda. Let's see, let's just drop the relaxation time to a small value, and I'm plotting to 500,000. Let's see what happens. Boom, it reaches the limit of the spring very quickly. And then that's as far as that spring went. So a small relaxation time, it gets there fast. So a small relaxation time, right, means that E2 is going to be a lot bigger number. It's dominated by the spring. And then if we make this a really big number, which means that lambda viscosity is a really big viscosity relative to that, then this it looks like it's a linear function. No, it's still that curve, but I may need to go out to 50 million seconds. Let's see. It's still, now you can see it's starting to curve over. Let's go to 500 million seconds. Okay. So it's the same function, the same shape. Conceptually, but there's just a time scale that changes depending on the relaxation. But it's always going to have that shape, per se. So experimentally, we don't have, let's see. So let's say if we do a test, we got 60 seconds in a minute times 60 minutes. Actually, we're going to do it this way. We won't use Mathematica. We'll use our Mac. 60 seconds in a minute times 60 minutes in an hour times 24 hours in a day. So 86,000 seconds per day times, we do test 90 days, 8 million seconds would be kind of a long test. Let's go to 300 in a year. 365, well, 31 million seconds. If these units are pounds per square inch. All right, so $410. Why don't I stop there rather than trying to hammer through this? We'll pick this up and work with some real data files on Thursday. Okay?